Okay, so today I was asked to talk about Vsepr theory, which is Vsepr theory, and that stands for valence, shell, electron, pair repulsion theory, which sounds fairly complicated, but it's actually a pretty easy idea. Essentially, every group of electrons around a central atom wants to be located as far away from each other as possible to minimize repulsions. And so those repulsions maximize the space that each atom or lone pair is attached to the central atom. And it results in 5 what are called electron group arrangements. And those gives rise to different molecular shapes. And I'll explain that as we go along. So prior to this lecture, we would have talked about how to draw a Lewis dot structure. So I'm assuming everybody knows how to draw a Lewis dot structure. I'll show you how I actually draw them as I go through examples. And I think the best way to do Vsepr theory is to actually go through and do different examples. So what I'm going to do is I'm going to start with some simpler molecules first, and then work my way up to some more complicated molecules. So the first molecule I want to show is HCN. And if I was going to draw a Lewis dot structure for this, I'd count up the valence electrons first. Hydrogen has 1. We know that from the periodic table. Carbon has 4. Nitrogen has 5 for a total of 10 valence electrons. Then the least electronegative element is put in the middle. In this case, it's going to be the carbon. And I always tell my students never put the hydrogen in the middle, and I make them promise this because you can't have hydrogen in the middle and you can't have any more than one single bond attached to it. So we're going to go carbon, and we're going to put the nitrogen on one side and the hydrogen on the other side. And then we're going to fill in the lone pairs. And we're counting up how many electrons we drew. So if I count correctly, there's 2, 4, 6, 8, 10, 12, 14. And so what I'm going to do is, that's too many, right? So I'm going to add multiple bonds here. So let's erase some of these guys. And what I'm going to do is I'm going to put a triple bond in there, like so. And count them up. So I got 2, 4, 6, 8, 10. So that's a good Lewis dot structure. So we're going to focus on here. I'll put my little eyeball. That's a little eyeball. Is we're going to focus on that central atom and what's attached to it. And in this case, there's what are called 2 electron groups attached to it. Now, an electron group can be anything like a single bond, a double bond is an electron group, a triple bond is an electron group, a lone pair of electrons are an electron group. In this case, we've got 1 electron group, 2 electron groups. And so when we have 2 electron groups, the electron group arrangement is called linear. Because the farthest that 2 electron groups can get away from each other is a straight line. And so then the bond angle between these is obviously 180 degrees. Now there's no lone pairs there. So the electron group arrangement is the same as the molecular shape. Which is also linear. Now, when we have lone pairs around that central atom, that's going to change. The electron group arrangement is going to be different than the molecular shape, but we're going to get to that in a minute. So that's the easiest shape to draw. Okay, so let's go on. Let's do something that's a little more difficult. Not much difficult, but a little bit. We're going to do boron trifluoride next. So BF3. Obviously, boron goes in the middle. Fluorine's the most electronegative element in the periodic table. So I'm going to put the boron in the middle, surround it with the fluorines. Let's erase that. I didn't mean to put that little dot in there. Let's get rid of that. And I just took off some of my boron. That's not good. So I forgot to count up the valence electrons. So boron has 3, and each fluorine has 7, but there's 3 of them. So that's 24. Lone pair, lone pair, lone pair. So just filling in octets. Now boron is one of the interesting atoms in that it doesn't actually have to have an octet. So this is an exception to the octet rule. So we're gonna leave that the way it is because we count up the valence electrons. We've got 24. Now we have 3 electron groups attached to that central boron. We've got each fluorine has a single bond, so that's 3 electron groups. And so the question is, how do 3 electron groups get as far away from each other as possible? Well, it turns out it's like the corners of a triangle. So the electron group arrangement here is called trigonal planar. And because there's no lone pairs in the central atom, the molecular shape is also trigonal planar. And again, if there was a lone pair in the central atom, that electron group arrangement is going to be a little different than the molecular shape. And again, we'll get to that here in a minute. Okay, so that's 3 electron groups. Now what happens if we have 4 electron groups around the central atom? So the one you usually show for this one's like methane. Carbon has 4 valence electrons, hydrogen has 1, but there's 4 of them. It's for a total of 8. Carbon obviously goes in the middle because everybody promised me they would never put a hydrogen in the center of the atom. So you count up the valence electrons. There's 8 in that Lewis dot structure, so that's a good Lewis dot structure. Now when you look at that, it looks like the farthest the hydrogens can get away from each other is a 90-degree angle, so it looks like it's a square shape, but it's not. Because you got to start thinking about these molecules in 3 dimensions. So I'm going to draw this like an organic chemist would draw it. The little wedge and dashed lines, let's draw those 2. The wedge means that the hydrogen is sort of poking out the front of my iPad. The dashed line means that the hydrogen is poking into the center of the iPad. I've got the hydrogen on the top and the hydrogen on the side, which are in the plane of the iPad. And so when you look at that, you can sort of imagine it looking like a tripod. So you've got the 3 legs on the bottom of the tripod with the hydrogens attached. And then you got the last hydrogen attached off the top. And so the electron group arrangement, because there's, let's go back, sorry. The electron group arrangement, because there's 4 electron groups, so 1, 2, 3, 4. So the electron group arrangement is what's called tetrahedral. There's no lone pairs in that central atom, so the electron group arrangement and the molecular shape are the same. Now, it turns out that the bond angles here are 109.5. And I think I forgot to say in the last one that the boron trifluoride molecule, the bond angles on that one are actually 120 degrees. Okay, so that's tetrahedral electron group arrangement. Now let's actually start adding some lone pairs onto that central atom. So the one I want to show next is ammonia, which is NH3. Nitrogen has 5 valence electrons, hydrogen has 1, but there's 3 of them for a total of 8. Nitrogen obviously goes in the middle. And then we've got hydrogens attached on the outside. We're going to fill the octet on the nitrogen. Okay, so we still have 4 electron groups. So 1, 2, 3, 4. So we still have your electron group arrangement being tetrahedral. because there's 4 electron groups. However, you've got a lone pair, so now the molecular shape is actually going to be different. So let me draw out the tetrahedron. This is a generic tetrahedron, again with the dashes and the wedges, and I've got the hydrogens here, 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 and I got my lone pair on the top. Now I know there's not a physical bond attaching that lone pair to the nitrogen, but I just put the line in there so you can see the generic tetrahedron. And the key to this one is that those electrons are small compared to the atoms, so we're just going to pretend that they're just not there. And when you pretend they're not there, that actually changes the shape. So different books have different names for these. The one I'm going to call this, so molecular shape, I'm going to call this pyramidal. So this is illustrating how when you have a lone pair instead of all atoms attached, the electron group arrangement is actually different than the molecular shape. Okay, let's keep going. The next one I want to show is water, because water is obviously very important, so it's nice to know things about water. Hydrogen, there's 2 of them. 1 valence electron for hydrogen, and you got oxygen is 6, so that's a total of 8. Oxygen obviously goes in the middle. So oxygen, hydrogen, hydrogen. Fill the octet on the oxygen. We count up the valence electrons. 2, 4, 6, 8. So we're good. We've got 4 electron groups, but now instead of 1 lone pair, we've got 2 lone pairs in that central atom. So again, let's just draw the generic tetrahedron here. Lone pair, hydrogen, hydrogen. We're going to use the same trick as we did before, where we're going to say we don't really see those. And so this gives rise to a new molecular shape. So the electron group arrangement here is still tetrahedral, because there's still 4 electron groups. However, because we have 2 lone pairs, the molecular shape is going to be different. And now the molecular shape is going to be what's called bent, because it looks like a kind of like a V. Some books call it V-shaped. I always kind of learned that as bent. So what's interesting about the bond angles is, we said in a tetrahedron where you have all atoms attached, so I'm just going to draw a generic one. So X is not an element. Y is not an element. This was 109.5. If you remember from the example I showed with methane. So what happens is when you start adding lone pairs of electrons, that actually squeezes that bond angle up slightly. So the ideal bond angle for a tetrahedron is 109.5. Well, these guys, when they have lone pairs like that, it's going to be less than 109.5 degrees. Okay, so I only have a minute left in this video, and depending on what chemistry class you would take, from me, I teach 2 different kinds of chemistry classes. I teach general chemistry classes. I teach nursing, general chemistry, and I teach the chemistry for the majors and the doctors. The nursing chemistry would not go beyond this. So what I mean by not go beyond this is you can actually have expanded octets, which means you can have more than 8 electrons around the central atom. We're not going to go there because I don't have enough time. So I've shown you everything up to when we start to expand the octets. So I hope I can upload this to YouTube, because it's going to be my first time. And thanks for listening. And if you have any questions, please don't hesitate to ask. Thanks again.